Hello, my name is Zahra Khanian, and I'm a postdoctoral researcher at the Technical University of Munich. I am going to talk about quantum state redistribution for ensemble sources, which is a joint work with Andreas from Autonomous University of Barcelona. First, I'm going to give an outline of my presentation. Okay, I'm going to start with introduction to quantum source compression problems because, of course, quantum state redistribution is a source compression problem. Later, I'm going to talk about our results in this context and discuss them. Okay, quantum source compression was studied by Schumacher for the first time in the 90s. Schumacher defined a quantum source as a quantum system together with correlations with a purifying reference system. In this model, the encoder, let's call it Alice, wants to compress many copies of system A. And by compression, we mean that system A is mapped to another system of a smaller dimension, of course, using general quantum operations, which are CPTP maps. The compressed information is then sent to a decoder. We may call it Bob, via noiseless quantum channel, who wants to reconstruct many copies of system A from the compressed information in such a way that the correlations with the reference system is preserved. We can define the rate of the compression as the logarithm of the dimension of the compressed information over the number of copies of the system. So here we denote the number of copies of the system with n. This is actually a general theme for any source compression problem that I'm going to discuss in this presentation. So it is first important to grasp this compression model. Schumacher essentially showed that the optimal compression rate for this specific model is equal to von Neumann entropy of the system A. Along with the purified source that he defined, he also defined another notion of a quantum source, which is basically an ensemble of pure states, which we can equally show it by a classical quantum state here. And here, the classical register X plays the role of a reference system that essentially we want to keep the correlations with. So another contribution of Schumacher in the same paper was to show that even by considering the ensemble model, the optimal compression rate is still von Neumann entropy of the system. Okay, Schumacher compression model was later extended to compression problems with side information. And by side information, we basically mean that an extra system which is correlated with the source, of course, and it might be available to the encoder or decoder or both of them. One important example is state merging, where source is a purified state, which is very similar to the purified state source of Schumacher. Here, system A is a system that we want to compress, and system B is the side information of the decoder. The optimal quantum compression rate for state merging, considering a noiseless quantum channel between the encoder and decoder, is equal to half of the mutual information between system A and the purifying reference system, R. Okay, also similar to the ensemble model of Schumacher, the ensemble model of state merging problem was considered by Ahn and co-authors in 2006, and the optimal rate for this general ensemble model was not found in general, and only the optimal rate was found only for special cases of this specific source. But the general problem remained open since then. Okay, so the most general pure state model where both the encoder and the decoder have access to side information was introduced by Devetak and Yard in 2009. And the compression of this source is mostly known as quantum state redistribution. And they find the optimal quantum compression rate for this problem, which is equal to the half of the mutual information between system A and the reference system given the side information at the decoder side. In our work, we consider the most general ensemble model, which includes as special cases all the models that I discussed and introduced so far. Here, system A is the system that we want to compress. System C is the side information of the encoder, and system B is the side information of the decoder. R and X here are reference systems. For example, here in this CQ state, if we have only one non-zero px, then we are going to have a specific model which is equivalent to the purified model of conventional quantum state redistribution introduced by Devetok and Yard. And similar to Schumacher compression and state merging, we are going to consider many copies of the system. To recap and also to introduce some other special cases of our model, I'm going to review them briefly here. So I already introduced Schumacher's both models and also state merging. The other important example is classical quantum Slepi and Wolf, which was introduced by Devetok and Winter in 2003. So they basically consider this ensemble model where they want to compress classical register X, given that the decoder has access to quantum side information A. So I also introduced the ensemble state merging and quantum state redistribution by Devetok and Yar. The other important example is quantum classical Slepi and Wolf, where we wanted to compress system A given that the decoder had access to this classical register X. And also the other important example is the interpolation between visible and blind Schumacher compression, where basically the encoder has access to this quantum system which can be either a classical system or generally a quantum system. Okay, here I am showing the task of the compression in this figure. So we also consider that Alice and Bob, which are the encoder and decoder, share entanglement in register A0 and B0. The rest of it I already explained. Maybe it's good to explain it again. We have system AN that we want to compress, and CN is the side information of the encoder. The compressed information is denoted by MN, is sent to Bob via this noiseless quantum channel, and Bob wants to reconstruct system AN by having access to side information system BN. And the overall goal of this compression task is, of course, to keep the correlations with the reference system, and we want the overall final state to be very close to the original state in some distant measure. Okay, as for the figure of merit, we consider block fidelity, where we want to keep the fidelity between n blocks of states. And the other figure of merit that we consider is per copy fidelity, that instead of keeping the fidelity for all blocks of states, we just want to keep the fidelity for each copy of the state. And of course, we can, by tracing out some unwanted systems, we can obtain per copy fidelity from block fidelity. That is, this block fidelity is less stringent than per copy fidelity, and therefore we expect to get smaller rates, smaller compression rates considering per copy fidelity. Okay, a single letter function appears in our compression rates, and to make connections with the rate of conventional quantum state redistribution task, let's recall its rate, which is equal to half of the mutual information between system A and the reference system given system B. Okay, we have a very similar quantity to this rate here, However, if we have our quantity is again a mutual information, which is very similar to this mutual information here. However, our quantity here involves an optimization. Okay, maybe first I'm gonna recall this definition of the source, which is an ensemble of states. And if we consider its purification, we call register X prime as the purifying register for this state omega. And we define this function Q of epsilon as the infimum of this mutual information. Here we have the reference system, and Z is a similar system to system A that we have here. But we are taking optimization over all CPTP maps, okay, which are actually single shot encoder and decoders. And these encoders take system A and C and maps it to system Z and C hat. And the decoder takes system Z, which is the compressed information and the side information, and basically reconstructs system A and B in such a way that the ensemble fidelity for each copy is preserved. Okay, and in this mutual information, we have system Z, which is basically the compressed information. That if we were to consider a single shot version of quantum state redistribution, then Z would be the compressed information there. So the important quantity here is the value of this function at 0, this function Q of epsilon, and also the limit of the function at 0, which I'm going to expand later and tell what is our optimal rates. Okay, first let's just review some properties for this Q epsilon function. So as you can see here, it is a non-increasing and convex function of epsilon, and we can show that it is continuous for positive values of epsilon. However, we don't know whether it is continuous at 0 or not. So, and the main reason for this actually is that we don't know. We cannot use compactness, for example, to show that it is continuous, because a priori there is not any dimension but for the system Z, which appears in the optimization. Okay, the main result of this work is that we find the optimal compression rate considering per copy fidelity, which is equal to the limit of the function. We already define it as Q tilde of 0, which is basically the limit of function Q epsilon at 0. And from considering block fidelity, we can find upper bounds and lower bounds. And the upper bound is the value of the function at 0, and the lower bound is the limit of the function at 0. Okay, so for achievability, I'm going to give some insights how we can achieve these rates that I have already introduced. So let's recall our source. We had the source omega, and the big omega was the purification of our source, and there was this encoder, one-shot encoder, E epsilon in the definition of Q epsilon function. Okay, and let's just consider its isometric dilation. Okay, which basically takes system A and C to the compressed information system Z, C hat, and also W, which is the environment system. Okay, if we apply this unitary on the system, on our state, we are going to obtain many copies of this specific state, which we call it sigma epsilon. Okay, and we are going to use a conventional quantum state redistribution for this specific purified state to send system Z from encoder to decoder. Okay, and from quantum state redistribution, we know that the optimal compression rate is going to be half of the mutual information between the sender, the references given the side information at the decoder. And then we essentially can show that if we apply this single shot the decoder D epsilon in the definition of Q epsilon function to n copies of system ZB at the decoder, we can recover the information and we can preserve the per copy fidelity. Okay, in order to show the achievability for Q0, we have a similar strategy except the fact that instead of using this E epsilon in the definition of Q epsilon function, we are gonna use the CPTP map with value of epsilon equal to 0. And essentially, we are gonna again use quantum state redistribution as sub-protocol to obtain this quantum rate here, which is equal to half of the mutual information between Z, the references, given B for this specific sigma 0 state. And we can show that with this strategy, we can preserve the block fidelity. Okay. As for the converse, I'm not going to go into the details of the converse proof here, but it's worth mentioning that we use standard information theoretical inequalities to bound our rate, actually the dimension of the compressed information, by this quantity here, which is basically, if we take an infimum here, we are going to obtain the Q epsilon function, okay? And then since we obtain this Q epsilon function, which appears in the bound here, then we are going to use some characteristics of this specific function to bound our rate. And we basically here use the convexity property of Q epsilon function to obtain at this inequality here. Okay, so in order to remind this Q epsilon function, let's just review it again. So we had this Q epsilon equal to infimum of this specific mutual information over all CPTP maps. Basically, they are one-shot encoder and decoders taking system actually A and C to the compressed information and C hat, and also a decoder which takes the compressed information and system B and reconstruct the side information and system A hat in such a way that the per copy fidelity is preserved for this specific omega. Okay. In general, as I mentioned before, system Z here is potentially unbounded. So, for example, we cannot use compactness to show that this function is continuous at 0 or not. And essentially, we don't know whether Q of 0 is equal to the limit of the function at 0. But maybe it is helpful to introduce another function, which is, again, a single letter function, which in general, it's not easier to evaluate, but in some special cases, we can simplify the function and we can fully understand these specific examples. Okay, so again, let's consider this ensemble source omega, and also consider that big omega is the purification of this state with this X prime as the purifying register. And we define the K of epsilon as the supremum of this mutual information. We have, again, similarly to the previous function, we have this one-shot encoder and decoder, which take the system A and the side information and maps it to compressed information, and the reconstructed side information together with the W, which is the environment system, and also the decoder, which is defined similarly, okay, in such a way that the per copy fidelity for this ensemble model is preserved. But unlike this Q epsilon function, we only have a mutual information between system X, which is a classical system, and system W, which is the environment system, and we have a supremum here. And also the important quantities here is going to be K0 and also the limit of the function at 0. Okay, in order to give some insight, we can discuss that this function is non-decreasing and concave function of epsilon, and also it is continuous for positive values of epsilon. But similarly, we have, again, problems to understand whether it continues at 0 or not. Okay, and in order to relate these two functions with each other, we can obtain this bound. We can show that Q of epsilon is bounded by this mutual information, which is actually the rate of conventional state redistribution for the purified source minus 1/2 of the K epsilon function. And if the system C, which is the side information at the encoder side, is trivial, then we have an equality here. Okay, an example when the system C is trivial is from this paper by me and Winter, where we can show that there we have this equality. So as I told before, this function k epsilon is not necessarily easier to evaluate than this function q of epsilon. However, there are some special cases that we can evaluate that. So for example, consider irreducible sources. And by irreducible, we mean that if we consider the ensemble model, none of the states from this ensemble are orthogonal to one another. In that case, we can show that for k of 0 is equal to 0 and it's equal to the limit of the function. Basically, we can show that this function is continuous at 0. And since it is continuous at 0, we can from the properties of this function here, maybe it is good to recall that. So since it is continuous, we can obtain that the optimal rate is equal to Q of 0. Okay. Another important example where we have a simplified rate function is for this Bell ensemble of Bell states. And this example is from the paper by An and the other co-authors from 2006. So let's suppose that we have an ensemble of Bell states with probability distribution Px. And of course, if we trace out this system B here, we are gonna obtain the same state for system A for any given x, right? Then we can easily show that this function k of epsilon is equal to 0 because essentially it is the mutual information between system X and W, and since system A doesn't depend on X, we can show that system W, which is obtained by processing system A, doesn't depend on X either. So in this specific case, we can show that the optimal compression rate, considering per copy fidelity and block fidelity, are equal to 1/2 of the Shannon entropy of the classical register X. Okay. In conclusion, I would say that we studied a very general theory of entanglement-assisted compression, considering per copy fidelity and block fidelity. Considering per copy fidelity, we show that the optimal compression rate is equal to the limit of the function q at 0, and considering block fidelity, we obtain this upper bound q of 0 and the lower bound, the limit of the function at 0. And of course, if we can show that these two are equal, that is the function is continuous at 0, then the optimal rate is going to be equal to the optimal rate considering per copy fidelity. One important thing to discuss here is that even though we have a single letter function for the rates, it is still an unbounded optimization. So we cannot fully understand specifically, for example, the dimension of system Z. And we cannot use compactness to show whether this is continuous at 0 or not. So it is very important to understand these properties of this specific function. So in summary, we want to understand whether it is continuous at 0 or not. And if it is continuous, as I told, this would imply that whether we consider per copy fidelity or block fidelity, we are going to obtain the same compression rate. And also the other important question here is that we consider Alice and Bob, the encoder and the decoder, share free entanglement between them. So, and we obtain the optimal compression rate considering this free entanglement between them. However, we don't know whether this entanglement is necessary to do the protocol or it's not. So it would be very interesting to show whether this entanglement rate that we discuss in the paper is optimal or not. Okay, thank you so much for your attention.